Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. Let us discuss the continuation for a previous video where we have discussed about the trees concept, right? And in today's session, we will be discussing about binary trees. This is an overview where we are going to discuss under this session. What is binary tree we will see. Then we will be looking into what are the different types of binary trees. Then binary tree representation also. I'll cover all these three concepts in this session. Let us see what is binary tree definition. Binary tree is nothing but it is a tree in which each node has at most 2 children. That means you may have a node. For this, it may have at most 2 children. It does not have any children, that is one case, or it may have 1 children, or it may have 2 children also. If this is the case, it is satisfying, then we are going to name it as a binary tree. Okay, and it is having the left child as well as the right child, as we have seen in the example, right? Thus, the order of binary tree is always 2. The binary tree order is nothing but where you are going to have the representation of left and right childs where we are representing. Based on that, we are going to represent the tree order is 2. Thus, in a binary tree, we are going to have 2 nodes, that is at most 2 nodes where we are going to have the left child, right child, and you may have a root node also. And each node has either 0 children or 1 children or 2 children. As I said, we have only one node. This is a root node and it does not have any children. You don't have any children for it, left or right. Or a node with 1 children or a node with 2 children. At most means you may have 0 or 1 or 2. Any of these will be representing the utmost, right? And a binary tree is either empty or consists of a node called the root node, where I am going to have a node like this. This is called the root node. And the other one is left and right subtrees or themselves are nothing but a binary trees. If I am going to represent a left subtree or a right subtree, right? And those itself is called binary trees. Okay. This is nothing but a binary tree. Let us take the example of a binary tree. Here, you are having a tree representation with all the nodes A, B, C, D, E, F and G, right? And a node with, as this tree is satisfying the binary tree properties or not, we are going to check. Yes, as we know that a binary tree is having at most 2 children. That means 0, 1, 2. These things has to be present for a binary tree. Now, you can check. Here, for this node, we don't have any children, right? No children with 0, right? Node with 0 children. Or you can see you have 1 children. A node with 1 children is also there. This is a node. It is having 1 children and a node with 2 children. That means here B is a node. It is having 2 children. Yes, this is a binary tree because it is satisfying all the cases. Coming to types of binary trees, here we are seeing all these types of binary trees. Under this, first we will be looking into left skewed binary tree, then right skewed binary tree, then we have fully or strictly binary tree, and we have complete or perfect binary tree, and at last we have almost complete binary tree. All these different types of trees we are going to look into. First, see about the left skewed binary tree. What is meant by left skewed? A left skewed binary tree is a binary tree that satisfies the following 2 properties. What properties it has to satisfy? First thing, it has to be a binary tree which is satisfying the utmost 2 children, right? And all the nodes in left subtree except leaf node has 1 and only 1 children, right? And the right subtree is empty here. Let us see this example. Here, a node with the left subtree, this is the left subtree, except the leaf node, except this leaf, this is the leaf node, right? You don't have any children for this. Except this node, The remaining all are having only one children. For A, you have only one children, B is having only one children, C, right? And you don't have the right subtree. Right subtree is empty. If you have the representation of tree like this is called a left skewed binary tree. Then coming to the right skewed binary tree, you may be knowing that this will be opposite to the left skewed, and it also has to satisfy the following two properties. All nodes in the right subtree except the leaf node has one and only one children, and the left subtree is empty. Let us see here, right? Except the leaf node, the remaining all nodes are having one children, right? Because of that, this is called a right skewed binary tree. And you don't have the left subtree. And the next one is full binary tree. A binary tree in which every node has either 0 or 2 children. We have seen binary tree is at most, that is 0, 1, 2. This condition has to be satisfied for a binary tree. But what is the condition for full binary tree? It has either 0 or 2 children. Only it should have either 0 children or 2 children. Then it is called a full binary tree. And a full binary tree is also called strictly binary tree also. Okay. Let us see here why this is called a full binary tree and why this is not a full binary tree. Now, why this is not a full binary tree? What is the condition here? The condition here is it must have 0 or 2 children. Every node have 0 or 2 children. Observe here. For A, you have 2 children. S. For B, you have 2 children. S. And for C, you have only one child. That's why it is not satisfying the property of full binary tree. And if you can see the same diagram here I have removed H. How I can make this tree as a full binary tree? If I am not having this node, then you can check every node is having either 0 or 2 children. This A is having 2 children, B is having 2 children, E is having 2 children, and for C, it doesn't have any children, but also it is going to satisfy the property of full binary tree. Okay. Next one is complete binary tree. A complete binary tree is a binary tree that satisfies the again two properties it is going to satisfy. One is every internal node has exactly 2 children. Every internal node, that is except root node and the leaf nodes, the other nodes are called the internal nodes. Those must have exactly 2 children and all leaf nodes are at the same level. Complete binary tree is also called as perfect binary tree. Let us see the example here. Yes, this is not a complete binary tree. Why? Because observe, for this it is not having exactly 2 children. For A, B and C are 2 children. For B, D and E are 2 children. But C, it doesn't have any children. But this is satisfying the property of full binary tree. Why? Because it is having 0 children. But this is not a complete binary tree. And when you are going to say it as a complete binary tree, to make this complete binary tree, for this node also it should have exactly 2 children. Then only we can say this as a complete binary tree. Okay. And the next one where you are going to look into almost complete binary tree. That means it will be comparing with the complete binary tree. Little bit small difference you are going to find. What is that difference? Almost complete binary tree is a binary tree that satisfies the following two properties. The first one, all the levels are completely filled except possibly the last level. If only the last level, it should not be filled. The last level must be strictly filled from left to right. It has to fill from left to right. Right? Let us see this one. This is not almost complete binary tree. Why? Because it is having all the nodes are at the same level, but it is not filling from left to right. It is on the right hand side. That's why it is not a almost complete binary tree. It has to fill the nodes from left to right. If we can see D, E, F, this has to be filled on the left hand side first, then if you are going to get any other node, that will be filled on the right hand side. This is the condition where it has to be followed in the almost complete binary tree. Okay, this is how where the different types of trees we have looked into. And see the properties of binary trees. What are the different properties we have? Here, the first property, minimum number of nodes in a binary tree of height h equal to h plus 1. How many minimum number of nodes should be there in a binary tree if we have given a tree of height h, right? Let us see. This one, you know that this is a left to skewed binary tree. What is the height of this tree? If you are going to see, the height is 4, right? How many number of nodes we can represent if I am going to have the height as 4? The number of nodes, minimum number of nodes can be, minimum number of nodes depends on the height, that is 4 plus 1, totally 5. 1, 2, 3, 4, 5, right? Totally 5 nodes are required for a tree with height h, that is 4. Next, if you can see the next property is maximum number of nodes of a binary tree of height h equal to, how we can find the maximum number of nodes it may consist of, right? It may consist of 2 power h plus 1 minus 1. That means based on the height of the tree, we can decide that how many maximum number of nodes can be present for a binary tree, right? For this, if you can see height equal to 3, if it has given height as 3, then based on that, by using this formula, we can say that maximum number of nodes that can present in a binary tree is almost 15 nodes. Wow, just you see here. This is the formula that was given, 2 power h plus 1 minus 1, that is h is nothing but 3. 3 plus 1 minus 1, that is 2 power 3 plus 1 is nothing but 2 power 4. 2 power 4 is 16. 16 minus 1, 15 nodes. You can check here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, totally 15 nodes are going to be present in a binary tree with the maximum number of nodes. And the next property where you have is total number of leaf nodes in a binary tree equal to total number of nodes with the 2 children plus 1. Right? Based on this, you can see, suppose I am going to have the number of leaf nodes equal to 3, number of nodes with the 2 children equal to 2, right? Observe here. Number of leaf nodes, how many leaf nodes are there? 1, 2, 3. 3 leaf nodes are there in this tree. This is equal to the total number of nodes with the 2 children. This can be equal to the total number of nodes with the 2 children plus 1. That means you observe which of the nodes with the 2 children. A is having 2 children and B is having 2 children and A is having 2 children. Right? This one plus 1, we are going to add 1 to it, that both will be equal. Right? Number of leaf nodes equal to the total number of nodes with the 2 children plus 1. This will be one property which it is telling you about. Next, fourth property, maximum number of nodes at any level L in a binary tree equal to 2 power L. Let us see this. You know that the level we are going to represent from 0, 1, 2, right? The maximum number of nodes at level 2 in a binary tree. Maximum number of nodes is this one, right? This is level where it is representing. Level is 2. 2 power 2 is nothing but 4. This is where you are going to find the maximum number of nodes that can be present based on the level wise. And the last one, number of different binary trees possible with n unlabeled nodes. Right? If I have not given any labels to my nodes like A, B, C something, then how many nodes we can draw or we can represent based on that, based on this formula. Right? 2n Cn by n plus 1, right? Based on this formula, we can able to construct 5 different type of binary trees we can construct, right? This is a 3 unlabeled nodes if you have given. Based on this, you can see 2n Cn, that is nothing but 2 into 3 Cn, that is C3 by 3 plus 1. That is nothing but 6 C3. 63 is nothing but 6 factorial by, that is n factorial by r factorial, or is nothing but 3 factorial into n minus r factorial, that is 6 minus 3 factorial is nothing but 3 factorial, right? This will give you the resultant of 3 factorial, 6 into 4 into 3 factorial by 3 factorial into 3 factorial. This will be cancelled. 3 factorial is nothing but 6. This 6 will be cancelled. 4 by, sorry, here you have 5, right? 6 into 4 into 5 into 5 into 4 into 3 factorial, right? Into 5, 4 will be cancelled. You are going to get the value as 5, right? That means 5 different binary trees can be constructed here. Let us see what are the different binary trees we can construct. Let us see here. Here we have the 3 nodes. Here we have a left skewed and we have a right skewed, and this is a normal binary tree and this is another one, right? Like this way we can construct 5 different binary trees from 3 unlabeled nodes. Like this way we can find it for the other, that suppose I have given 4 labeled or 5 labeled, we can able to construct the binary trees. Next one. Next we will be seeing about how we are going to represent these binary trees. The binary trees can be represented in 2 ways. One is by using array representation and another one is using linked list representation. Okay. First see about the array representation. Here array representation is nothing but the sequential representation or array representation, both are the same. If we have given a tree and how that can be represented in terms of an array, that we'll see. Trees or the nodes, tree nodes are stored in a linear data structure like array, and root is stored at index 0, and where we are going to place the left and right childs, that depends on this location of I. If node is at location I, then its left children is at 2 into I plus 1 and the right child is located at 2 into I plus 2. If the index representation is from 0 onwards, right? Please remember this. If I am going to start the index from 1 onwards, again this formula little bit changes, that is 2 into 1 and this is 2 into I plus 1. Let us see the diagrammatic representation of the tree. Yes, this is the array representation. How many nodes we have? We need to represent all the nodes in the array representation. My array index starts from 0 onwards, 0. Then for this it is having 2 children, 1 and 2. And 3 you have a children, is for 4 you don't have any children. Still we need to represent that empty space here. Right, 5 we have children, 6 we have children. Then 7 and 8 I don't have children. Right, 7, 8 are empty. And if I have a node here for this 9 and 10, these are empty. And for E, this is empty, right? And for G and for this also we have empty, 11, 12, this is 13 and 14. The empty spaces must be specified in the array representation. Why? Because if I am continuously representing my nodes in this particular array, then the tree representation is different, right? That's why we need to give the spaces, and according to that indexes, we need to fill this array representation. Now, what are the advantages of array or sequential or static representation of arrays? Any node can be accessed from any other node by calculating its index, and this is efficient from execution point of view. Where my particular child is present in my array, that can be easily identified based on these indexes. If that is not the case, there is no or less overhead of maintaining pointers. In the arrays, we are not using any pointers. Because of that, there will be overhead, there is less overhead in maintaining the pointers. And what are the disadvantages with the static representation? The major disadvantage with this type of representation is wastage of memory. First thing is wastage of memory. Example, in the skewed tree, half of the array is unutilized. Suppose if I'm going to have a left skewed binary tree or right skewed binary tree, in that particular case, I'm just representing only the left part. I'm not using the right part. In that case, all the remaining part of memory will not be used. Because of that, there will be the array is unutilized. Also, allows only static representation. There is no possible way to enhance the size of the tree. If it is of static, the size will be fixed and we are unable to increase the size also, right? We are unable to increase the size of it. That is the one more disadvantage you are going to find with the static representation. And inserting a new node and deleting a new node from it are inefficient with this representation because this requires considerable data movements up and down the array, which demands excessive processing time. If I want to insert a node or delete a node into the tree, it will be taking a lot of movements, that is up, down we need to move, right? Because of this, it will be taking excessive processing time. Because of this also, we can say this is one more disadvantage with the static representation of binary trees. Because of this, we are moving to the other way of representation. The most popular way to represent a binary tree is based on the linked list representation. Okay, each element is represented by a node that has two fields. One is the left child and another one is the right child. Okay, the space required by a node n binary tree is n into size of node. That means based on the size of node and n, we are going to calculate that much space will be available. Now, this can be done by using the linked list representation. Right? We have disadvantages with the array representation. That's why we are moving on to the linked list representation. Now, how the structure will be. As we have seen in the linked list representation, like single linked list, double linked list or circular linked list, these concepts, there how we have maintained the same structure. Here also we are going to do the same. The structure, data structure, the structure part will be taken as defining the structure of the binary tree, and based on that, the pointers, everything will be included. Let us see how we are going to have the binary tree linked representation. Node will be created, right? A node will be there. For this, you have the left child and right child, right? Left child and right child. And in between that, we are going to store the data. This is the node structure for a tree. And the pointer L child stores the address of the left child node, and the pointer right child stores the address of right child node, right? Here where we are going to store the address of left child, and here we are going to store the address of right child. And if the child is not available, null is stored. If I don't have any children, then this will be stored with null. And a pointer variable root represents the root of the tree. The pointer variable represents the root of the tree. This one is pointing to the root of the tree, right? This is how the linked representation will be. And here you can see the complete picture of how a linked list representation can be done for a tree. This is the root node, where this is the left child and right child. Here it is having the children, so that we are going to store the address of this 2000 here, and the address of the right child address will be stored here. And again, if these nodes are having the children, those addresses will be stored here, right? And if you don't have any children, we are going to store with all null values like this one, right? This is a tree representation for binary tree using linked list. Now, how we are going to write code for this, right? In stepwise, how we are going to make the creation of it. Similarly, like the linked list, how we have created, the same process we are going to follow. The first condition where we are going to check for whether the list is present or not, that is, the list is present or not. That is nothing but initially we are going to initialize root equal to null represents we don't have any linked list. Root equal to null represents list is empty. Now, whatever the node we are going to create, that becomes the root node, right? I want to create a node with the 10, right? This is the node creation, and the address of this one is 1000, and this is n, and the left and right childs are null initially. and the name of this node which we have created is root node. Initially, for the first time, if root equal to null, what you are going to do? We are going to assign the node which you are going to create, that becomes the root node, right? And step 3, if I am going to create one more node, that is 20. Node will be created by malloc function. N is the address, N is the name of the node, and 2000 is the address of it. And left and right childs are null here. And now I want to insert this 20 to the left of 10. That means I want to insert to part of this one, right? Now in that case, what happens? We are going to take some temporary variable for this, right? And assigning this part, this 20 part will be assigned to this one, right? Make note of this, and we are going to store 2000 in this location. Yes. Now we have made a link for these two. When I am moving this temp to this, why? Because I need to traverse through the list, we are going to use one temporary variable, right? Temp equal to temp arrow next, temp arrow left equal to n. This is my temp value. Temp arrow left is nothing but the n value. N is nothing but this one. Next, if I want to insert one more node, 30, the same memory allocation will be done. This should be assigned to on the right side of my tree. The same way, here we have temp. This is the right part of it. Make a link of it. Store the address of 3000 here. Temp arrow right equal to n, right? This is how where we are going to do. In the same way, if I want to create it for 40, now you know that this is your root node or a temporary variable. This is already you have done. Now we need to move our temp to temp arrow left. That means if I want to insert 40 on left of this, then I need to move my temp to this part. Temp equal to temp arrow left. Now temp will be moving to this location. Like this. I am going to assign, the same process will be repeated. 4000 will be assigned. Same temp arrow left equal to n. Right. The same code where you can see here. We are going to create a node by using malloc function, read the data value, and left and right child initially will be null and root equal to null. Root equal to n. That means initially whatever the node you are going to create, that becomes the root node. Else temp equal to root. That means we are assigning the root value to temp. Why? Because until temp not equal to null, we are going to repeat this process. What process we are going to do? We are going to take the choice as 1. If choice equal to 1 means we are going to insert the node on the left of the root node. If choice equal to 2 means we are going to insert the node on the right side of the root node. Temp arrow left equal to null. Yes, if you have not inserted any node on the left hand side of the root node, now we are going to do temp arrow left equal to n or current. That is whatever the node name you are going to use, that one we are going to specify and return. Right? That value should be returned back. If a temp is not equal to null, then we are going to assign temp equal to temp arrow left. Right? We have seen, right? First we have inserted 20. Based on that, it is going to check temp arrow left equal to null. Right? We have seen it. What we have done. This is null first. This is null. Because of that, we are adding this node here and returning back. And if it is not null, it is having some address. In this case, what I am going to do, if I have selected the choice as left choice, in this case I am going to assign this temp equal to temp arrow left. That means here temp will be, now it is moving to the temp arrow next. Now it will be again calling this node and it will be adding here. In the same way, the same process will be repeated for the right part also. Okay, this is how where the linked list creation can be done. And let us see the summary of today's session. What we have seen. We have seen about a binary tree. What is binary tree and how we can represent a binary tree, and what is the difference between tree and binary tree. These things we have discussed. And we come across the types of binary trees. We come across left skewed binary tree, right skewed binary tree, then full binary tree, complete binary tree, and almost complete binary tree also we have covered. And at last, we have seen about the binary tree representation. Here we have discussed about two binary tree representations. One is array representation and another one is linked list representation. In array, we have some disadvantages. That's why we have moved to the linked list representation. Okay. I hope you understand this concept.